Example 5. Find the horizontal or oblique asymptote, if one exists, of the graph of each function. All right, so again, we have 4 rational functions. We are interested in finding the horizontal or the oblique asymptote. Remember, it's not possible to have both on your graph. Your graph will either have a horizontal asymptote or an oblique one. Can't have both at the same time. It is possible for a rational function to have neither. Okay, going into this, we've already talked about vertical asymptotes. Some of these graphs may have vertical asymptotes as well, but we will not be finding the vertical asymptotes in this example. Okay. All right, in part A, our rational function is r of x is equal to 4x cubed minus 5x plus 2, all over 7x to the 5th plus 2x to the 4th minus 3x. Okay, in finding horizontal and oblique asymptotes, it's all about comparing the degree of the numerator to the degree of the denominator. So when I look at this particular rational function, the degree of the numerator, that's the highest power of x you see in the whole thing, it's degree 3 over degree 5. Okay, so what we see here is that the degree of the numerator is smaller. Okay, so if we go back to our rules on the previous page, okay, we've got to read through our different cases. Okay, we need to find the case where the degree of the numerator is smaller than the degree of the denominator. Okay, that's right here, the one that's highlighted in blue. If the degree of the numerator is smaller than the degree of the denominator, then the graph has horizontal asymptote y equals 0, which is the equation of the x-axis. So there is no work to do. You can automatically write that it's going to be a horizontal asymptote, and it's going to be at y equals 0, which is the equation of the x-axis. Okay, again, you could type this equation into your calculator, graph it out, and see if you observe a horizontal asymptote at the x-axis. Okay, on the next page, I do have all of these functions graphed out for example 5. Here is the graph of the function in example 5a, and you can see, like, the graph, this is kind of a complicated graph. There's actually 4 blue pieces, 4 disjoint blue pieces. But if you travel along this piece, okay, so if I'm going this way, eventually you get closer and closer to the x-axis without touching it. Okay, it is possible to cross a horizontal asymptote, but that's not happening here. You got to really zoom in here. You can see the red dotted line on the x-axis. Okay, same thing if you travel in this direction, your graph goes up and then it starts coming back and hugging the x-axis. Okay, oh, actually, I take back what I said earlier. We do cross the horizontal asymptote here. You can see that this piece right here actually does cross the asymptote. Okay, so it is possible to cross your horizontal asymptote. Okay, but this particular graph, the leftmost piece and the rightmost piece, they kind of travel up, they go above the x-axis for a split second, and then they come back down and start hugging the x-axis. So the x-axis, which is y equals 0, is a horizontal asymptote here. Okay, all right, on to the next one. Okay, we can move on because part A, because that function has a horizontal asymptote, it's not going to have an oblique one. All right, moving on to the next rational function. Okay, h of x is equal to 3x to the 4th minus x squared over x cubed minus x squared plus 1. Okay, again, it's all about comparing the degree of the top to the degree of the bottom. All right, the numerator, the highest power of x is 4, so this is going to be degree 4. And the bottom is going to be degree 3. Okay, so the degree of the top is bigger. Okay, go back to our rules to figure out what situation this is. Okay, so if we look under horizontal asymptotes, we're looking for, we have numerator is smaller. Step 2 here is when the numerator and denominator have the same degree. That's not what's going on here. In the purple, if the degree of the numerator is bigger than the degree of the denominator, which is what we have here, okay, we can conclude there's no horizontal asymptote. Okay, so I'm going to come back over here. We know that there is no horizontal asymptote, but we do need to check on oblique. Okay, so let's go back and look under oblique. Okay, remember there is one specific instance in which you get an oblique asymptote, and that is if the degree of the numerator is exactly one more than the degree of the denominator. Okay, that is what we have. The degree of the top is exactly one more than the degree of the bottom. Okay, so we are going to have an oblique asymptote here. Okay, we have to find it. Okay, it's going to be some slant asymptote that has the format y equals mx plus b. Okay, you have to calculate it through long division. Okay, all right, I'm going to erase this because I need the room. I'll rewrite it when I post the notes. Okay, you have to do long division. Okay, so we're going to take the top and divide it by the bottom. Okay, so when I look at the numerator, I am starting with the fourth power. You've got to put a placeholder if you're missing any of the powers of x. So here you're missing the third power, the first power, the constant. So this is how we're going to set it up. Okay, I've got 3x to the fourth. I'm missing the third power, so I'm going to put a placeholder. So I'm going to put plus 0x cubed minus x squared. I'm missing the power of x, so I'm going to put plus 0x. And then I'm missing the constant, so I'm going to put plus 0. Okay, got to put those placeholders or it will not come out correctly. Okay, we are dividing all of this by the bottom, which is x cubed minus x squared plus 1. Okay, here we go. Okay, the first thing you're going to do is you're going to compare. Okay, you're going to say, if I look at this, what do I need to multiply x cubed by to get 3x to the fourth? Okay, well, I've got to multiply by 3, and I've got to go from the third power to the fourth power, I've got to multiply by x. So basically what I'm doing here is x cubed, which is x times x times x, times 3x. That's going to give me 3x to the fourth. Okay, so that's what's going to go there. All right, so now what you do is you multiply. I've got to take 3x and multiply it by x cubed, by negative x squared, and then by positive 1. Okay, so 3x times x cubed is 3x to the fourth, and then 3x times negative x squared is going to be negative 3x cubed. Okay, and notice I'm writing the fourth power under the fourth power, the third power under the third power. Now when I do 1 times 3x, that's just x to the first power. Well, sorry, I said that wrong. 1 times 3x is going to be 3x, and I'm going to write it right here in the x column. Okay, so it's going to look like this. Okay, think back to doing long division of just numbers. Okay, you have to subtract this step out. Okay, so I kept everything with the appropriate sign, but now when I come back and subtract this out, it's going to change the sign of everything. So this is positive, it's going to change to negative. This is negative, it will turn positive, and then this guy is going to go from positive to negative. Okay, all right, so now we see what's left. 3x to the fourth minus 3x to the fourth, those guys cancel. 0x cubed, which is 0, plus 3x cubed is going to be 3x cubed. I'm going to bring this guy down, minus x squared. And then 0 minus 3x is going to be minus 3x. Okay, and if you bring down the 0, you don't really need to because it's essentially nothing. Okay, so now you compare again. Okay, what do I need to multiply x cubed by to get 3x cubed? Okay, so I need to multiply by positive 3. Okay, we're going to do the same thing. We've got to take the 3 and multiply it through x cubed minus x squared plus 1. Okay, so 3 times 3x cubed is 3x cubed. Or sorry, 3 times x cubed is 3x cubed. And then 3 times negative x squared is going to be negative 3x squared. And then 1 times 3 is going to be 3. I'll put that over here in the numbers column. Okay, and then you're supposed to subtract out this step, so you need to change the sign of everything. This will go negative, positive, negative. Okay, and then you add 3x cubed minus 3x cubed is going to be 0. That will cancel. Negative x squared plus 3x squared is going to be 2x squared. You can bring down the negative 3x and the minus 3. Okay, and this looks really complicated because, you know, now if you try to compare it, how many times, what do you have to multiply x cubed by to get 2x squared, that kind of doesn't make sense. What you need to do at this point is stop, okay? Look at the quotient. Look at the quotient. It is of the format y equals mx plus b, okay? Here's your oblique asymptote, okay? So my oblique asymptote here has the format y equals 3x plus 3, okay? You had to do this long division process to get it, okay? Once you get the mx plus b popping up in the quotient, you're done. You don't have to worry about all the garbage that remains, okay? All right, I'm going to go to the calculator. We can see this better. I do have this function graphed on the next page, but we can see it better on the calculator. So I'm going to go to my calculator. I'm going to type in the numerator. So 3x to the fourth minus, let's see, x squared. Whoops. All right, so minus x squared, close parentheses, divided by open parentheses. I've got x cubed minus x squared plus 1, close parentheses. Let me double check that. Yes. Okay, here we go. So I'm graphing this thing, okay? I am not only going to put the rational function on here, but I'm going to move to y2, which is going to show up in red, and I'm going to put the equation of the oblique asymptote, which is 3x plus 3. Okay, so the graph of the rational function will show up in blue. That's what this color thing is for. And then the oblique or the slant asymptote should show up in red. Okay, I've got my standard window, and here we go. All right, so you can see it, okay? For this particular piece right here, this bottom piece, that's where the oblique asymptote is really hugging the function down here, okay? Up here, not so much. We're actually crossing the oblique asymptote up here, but this is considered an asymptote because on this lower piece, the graph gets closer and closer to the oblique asymptote, to that red line, okay? It's hugging it. Okay, so it is an oblique asymptote. If you look at the next page, okay, this is more of a zoomed out photo of the graph. You can see the same kind of thing. It's down here where it's asymptotic, where you're getting closer and closer to that line. Okay, and up here we're just crossing the asymptote. Okay, but that is how you find your oblique asymptote. It's going to exist if the degree of the numerator is exactly one more than the degree of the denominator, and you find it through long division.